All right, hey guys. So what we're gonna be doing in this video is we're gonna be doing exam 2, where we're gonna be working with the pipe network flow. So let me just pull up OneNote real quick. So what this problem has is, let me move my face out of the way real quick. So what this problem has is a network of 5 nodes. So we have node 0 here, node 1 here, node 2 here, node 3 here, and node 4. Where node 0 is connected to node 1 and 2, node 1 is connected to 2 and 3, node 2 is also connected to 4 and 3 to 4. Node 0 and 4 are external, and their pressures are 2 times 10 to the 5th pascals for node 0 and 0 pascals for node 4. And then each of these pipes will have different lengths. So for example, this one from 0 to 1 is 1.5 meters with a K value of 1.5. Now all these values are stored in the exam question. So for example, node 0 to 1 has a length of 1.5 and a K of 1.5. And from 0 to 2, it's 2 and 2. From 1 to 2, it is 1.5 and 0. From 1 to 3, same thing, 1.50. Then 2 to 4, 0.50. And then from 3 to 4, it is 3, 2. So, and one more thing, all of these have a Z, or depending on how you look at it, a height of 0 meters, except for the node 0, which has a height of 30 meters. I must forgot to add that. Okay, so with that, we can now sort of start with our first formula. So to find what we're trying to do with this network is we're trying to find the net flow between all these, so that, the net flow between all these and the pressure at each node. We're also trying to find the flow between all these pipes. So the pipe 1, pipe 2, pipe 3, so on, all the flows in here. And so to do that, we have our frictional heating equation, where it is the outlet minus inlet of pressure over rho for density, plus the change in Z over gravity is equal to negative frictional heating. Now we can also write frictional heating as velocity squared over 2 times our K value plus 4 frictional factor length over diameter of the pipe. So for our case, this first heat thing here is, we're going to call this delta head, which we'll do delta H to represent delta head. And frictional heating, so I'm going to do velocity squared over 2 K plus 4F L over D. Negative sign right there. So that's our first equation. So to find our delta head, we need this. But to find delta head, we need the frictional factor. And to find frictional factor, we're going to use our good friend, Google. So let me just pull up my browser real quick. Friction factor. All right, friction factor. Takes us to a Wikipedia page, and what we're going to be working with is the fanning friction factor. So there are two types of friction factors, the fanning friction factor, which we'll be using for this equation, and we have the Darcy friction factor, which if we go back real quick, not that one. Then the only difference between the Darcy and the fanning is the Darcy is 4 times as big as the fanning. But if we go down here, and what we're going to be doing is we're going to be using this equation in our script. So the first thing we need to do is we're going to need to import a couple things. First is, of course, NumPy as NP. And then from our good old buddy scipy.optimize, we're just going to import Newton and root. Now, all Newton does is it finds the zeros of a function by using the Taylor series expansion, but we're also going to bring in root, because if you try to use Newton on a function and it reaches too many iterations, I believe the cutoff is 50, it'll raise an exception, and you will not be able to get a result from that. So that's why we're going to be using root as well. So next thing we're going to do is we're going to import all our constants. So gravity is 9.81. The density of our fluid is 1,000 kilograms per meter cubed, so basically just water. Our viscosity, wrong one, is 1e to the negative third Pascal seconds. And then our diameter of the pipe and our roughness of the pipe. That's it. So our first thing we're going to do is we're going to find the friction factor for our function using Reynolds number. Let me reset my runtime real quick. I think there is some extra functions from before leaking back onto here. Okay. But so what's going to happen now is we need to do an A calculation and a B calculation for these two. So for our A, it's going to be 2.457 times the natural log of 7 divided by the Reynolds number raised to the 0.9 plus 0.27 multiplied by the roughness of the pipe. So, excuse me. And all this is raised to the -1. And then the entire value of A is raised to the 16th. B, same thing. The 37350 divided by Reynolds number. Let's see if I got that right. 37530. Just a little dyslexic. That is also raised to the 16th. And so our friction factor is going to be 2 times this expression, which is 8 over the Reynolds number raised to the 12th plus a plus b raised to a negative 1.5. And all this is raised to the 1 over 12. And so just to make sure this works, we plug in a Reynolds number of 1 and input our roughness, name ED. Oh, shit, I forgot to run all of these. Yeah, that's right. All right, so we get a value of about 16. So it works. No exceptions are raised. So what we need to do from here is we go back to OneNote. We need to plug it into this equation to find our delta head. So our d head function is going to take in our velocity, our k, our length, and our diameter. Although it might be easier to substitute the velocity out to give us flow rate. Because if you remember, velocity equals 4 times the flow rate over pi d squared for a circular pipe. So if we plug this in for here, we can input flow rate because the rest of these are constants. So what we're going to do is flow rate, which is Q, our length, our K, our diameter, and our roughness. I'll plug this in, and we are going to first calculate velocity based off our Q value. So we're going to take the absolute value because what's going to happen is we're going to use our V value to calculate our Reynolds number. And Reynolds number, it needs to be positive. So if we have a positive velocity, when we plug it into our Reynolds number, we get a positive Reynolds number. And then all the equation is for the Reynolds number is just rho density times velocity times the diameter over hold on, I'm having a brain fart here. Give me 1 second. I want to say it's gravity. Let me pull up our good friend Google again. Reynolds number equation. Okay, I was very wrong. Okay. So Reynolds number is not this. Let me just delete this. Nothing like having a brain fart. But anyways, so we come back here. So Reynolds number is just rho density velocity times the length of the pipe over the viscosity of the liquid. So there it is. What's going to happen now is we have our rho times velocity times length divided by viscosity. So going back here, we can do 4 times Q over NP dot pi times diameter squared. All right. So now we can plug those values into our delta head equation right here on OneNote. And what we need to do is we need to get the direction of the delta head. So we're going to do the sign of the flow rate. So for example, if it's going from positive, if it's positive, it'll go from the from node to the to node. So from 0 to 1. If it's negative, it'll be going in reverse. So if it says 0 to 1, it's actually going from 1 to 0. We need the negative np dot sine of q multiplied by velocity squared over 2 times gravity. Actually, did I remember to put gravity on here? I did not. Okay. So what happens here is actually, so gravity is actually shifted to this side of the equation because it's not divided. I don't know why I put that. It is the change in z multiplied by gravity. So what happens is the entire equation on this side is divided by g, so we get frictional heating over g, and this is our delta head. So go down here. So that's where our 2g comes from. I just got to put it in at first. So what happens here is we got our velocity squared over 2g. Now with the inside of the parentheses, which is just the k values plus 4 times the frictional factor, let's do the Reynolds number times the roughness. I mean the Reynolds numbers and the roughness multiplied by the length divided by the diameter. So if we calculate our d head with a flow rate of 1, and if we just do our very first pipe, which it has a length of 1.5 meters, a K of 1.5, a diameter of 0.1, and a roughness of 0.001. We run that, we get a value of negative 1482. So it returns a value. So far, so good. Now that we have that, what we're trying to do now is we need to calculate the flow. So to do that, what we're going to do is we're going to make another function called flow, and we're going to input our delta head, our length, our K value, our diameter, and our roughness again. And what's going to happen here is we're going to change the equation up a bit. So we got our equation down here. We have our delta head equal to negative velocity squared over 2g times k plus 4f L over d. So what's going to happen is, notice how our flow rate is kept inside this velocity. So if we manipulate this equation, we get 2g delta h over k plus 4f L over d equal to negative velocity squared. So oh, that's not going to go. Oh Lord, what happened? Where'd my pen go? Okay, so what happens is this is equal to negative velocity squared. So if we go down, we don't want the negative in here. So we want this positive. So what we're going to do is we're going to take the sign, or the negative sign, of delta H, and we're going to multiply it by the square root of 2g delta H over K plus 4 plus, multiplied by L over D. That's an F, not a plus. That's going to be equal to our velocity. Keep in mind our flow rate is 4Q over pi d squared. So if we get Q by itself, what happens now is, let me go ahead and scoot down some more. We have the negative sign, or the opposite sign of delta H, multiplied by pi d squared over 4 multiplied by the square root of 2g delta H, delta head, over K plus 4F L over D. So what we need to do here is we need the absolute value of delta H. So dH absolute value is mp.abs dH. Now what we're going to be doing is we're going to plug this into our Newton solver. Now the Newton solver, the smaller the value gets, the harder it is for it to converge. So I believe the cutoff for it is 1e to the negative 10th. So if dH absolute is less than 1e negative 10, return 0.0. So the 0.0 just basically force it to converge. So our next, well, not force the thing to converge. We're using Newton inside the function, I should say. So the function we're going to call f root, and we're going to declare it using anonymous functions. We're going to be plugging in our flow rate Q. So this is where we're going to be using our delta head function. Sorry about that. Delta head. All right. Ringer's off. Hopefully it doesn't do that anymore. So length will be what we're plugging into our function, K, diameter, roughness. And with that, what we're going to be doing now is we're going to be plugging that into our Newton solver. So we're going to call this calc flow, the Newton, our function, f root, and then our initial guess. So we're just going to go and type Q guess. So to calculate our Q guess, basically we're using this equation right here, minus the sign, because we're getting a positive. So basically all that we need to do is Q guess is equal to NP dot pi times diameter squared over 4 multiplied by the square root of, let me pull up one minute again. So 2, get that out of the way, 2 times gravity times our delta head absolute value. We're going to divide that by our K value plus 4 times 0.01. I'll explain that in a second, times length divided by diameter. So you recall, so go back to our fanning friction factor, and you notice this graph right here. Try to zoom in a little bit more. So if you see, we have our Reynolds number on the x-axis down here, and our friction factor on the y. notice all of our values right here are right between 0.002 and 0.01. So if we do 0.01, that gives us a reasonable guess. So that's why our friction factor is using 0.01. So F is equal to 0.01. And finally, what this function is going to do, so like we discussed in the OneNote, we're going to do the sign of our delta H, or the negative sign, multiplied by our calculated flow. I don't know why, but I had a brain fart there again. Okay, so what I'm going to do is I'm going to set a test variable set equal to d head, where the flow rate is 1. Five d e. And so what's going to happen here is with this test value, we are going to call our flow function, and what's going to happen here is plug in test our length 1.5, our k 1.5, d e. Okay. So let me look at this real quick. So what should be happening is we should be getting our Q value. So this should be returning about 1. So let me look at this real quick. That's why I forgot. Okay, so to get this to go to 0, we need to take the calculated value and subtract it from the absolute value. So if we do this again, flow, test our length, which is 1.5, k 1.5, our diameter, just d, and our roughness, which is ed. Okay, so negative, so it should be positive. So let me remove this negative sign. Right, so we get our flow rate extremely close to 1. So where I screwed up here is we don't want this negative sign. So we just sort of just like toss it into the trash can. All right. So now we have that figured out, we can now use you create another function called calculate the flows, or just calc flow. I'm going to use we'll be using something called head values. Actually, it might be easier if I do this. So what I'm going to do first is I'm going to copy paste this into our script. Okay. So notice from this column, so the first column is our from node. Our second column is our to node, so from 0 to 1. Third is our length, so from 0 to 1, the pipe is 1.5. And then the fourth column is our k value, or the summation of k throughout the entire pipe. So we got 1.5 from 0 to 1, 2 from 0 to 2. So we can use NumPy to basically break this up into different arrays. The before I do that, I'm going to go ahead and create our Z array. So we have 30 meters for our first node, node 0, and then just 0 for the rest. So we got node 1, node 2, node 3, node 4. Run that. So what's going to happen now is, well, let's go ahead and create our external pressure array. Where we have 2 each of the 5th pascals and 0 pascals. Now this is for node 0, this is for node 4, because those are the 2 external. We'll go ahead and denote here external node. np.array and go 0, 4. Node 0 and node 4 are the external nodes. And to get our internal, to get our internal nodes, what we need to do is we need to find the number of nodes. And to do that, what we're going to do is types all of the arrays, and we're going to want the first index. So not the first value, but index 1. And what we're going to do is we're going to take the max, we're going to add 1 to it. Because the number of nodes is 1 more than the max. So there are 5 nodes, and then this just goes up to 4. So now to get our internal nodes, what we can do is we're going to be using the set function, and we're going to do the range of n nodes. And we're going to be subtracting the external nodes. So okay, I see what happened here. So what happened is this is being interpreted as a float. So give me 1 second. Let me just put this on Do Not Disturb. So as type np.int32. Right, so if we're in the range, so 0 to 5. Now if you look at the internal nodes, you're going to see 1, 2, 3, which are the internal nodes. So go back up to the top. Okay, there we go. So yeah, so node 0 and 4 external, 1, 2, 3 are internal. So now we have that. Now let's break up each column. So the from nodes is going to be equal to types, all the arrays, 0th index. The 2 nodes, same deal, types, index 1. Our length equal to types, all the arrays. Excuse me, I'm having heartburn. Second index. And then our k, which is pipes, all the arrays, 3. Then just to make sure it worked, from nodes, helps if I could spell correctly. Two nodes, make sure just none of them are empty. All right, so with that, what we can do now is we can create the heads array, which we'll be using to calculate the flow. So number of nodes. So all that MP0 does is it creates an array of 0 for that number of indexes. So number of nodes, so we have 5 nodes, so we have 1, 2, 3, 4, 5 values here. So what we're doing now is we don't know what the head value is for the internal nodes because we need to know the flow. However, we can find out the head for the external nodes because we know both the pressure and the Z. And if you go back here, scroll down again, it's a little messy. If you remember, our frictional heating over gravity is our DH, or delta head. So we have our pressure over rho G plus C. So we can, for our external nodes, we can calculate our delta H by using our external P array over rho times gravity and adding our Z external nodes. So this will only take the 0 and the 4th index, so 30 and 0. So if we look at heads again, we get a head of 50.387 for our very first node, node 0, and a head of 0 for our final. So if what we can do with this now is we can create our function calc flows, where we'll take in our heads array, and what we'll do is it will return all the flows. So but for our flows, instead of doing it by the node, our flows are by the pipe. So what we need to do is number of pipes is equal to pipes.shape 0. So let me go ahead and delete this real quick. Oh, we'll get back to it. But so number of pipes. So we have 6 pipes. 1, 2, 3, 4, 5, 6. And all pipes.shape is it looks at the pipe of the shape of the array. Help if I could spell. All right, so you can see we have 6 arrays, and each array has 4 elements. So if we take the first one, 6 arrays. That's what the 0 is for. So now we have the number of pipes. So what's going now is go back to calc flow, taking our heads array. Right, we have flows is equal to np.zeros. Once again, just creating an array of just zeros for the number of pipes. And then what's going to happen here is for I in range of n pipes is we're going to be calculating the flow of the pipe. So once again, this is why we have our flow right here, where it's going to return our Q. So the only thing we need now is we need to calculate our DH. So our DH is going to be our heads from nodes I subtracted by heads from nodes. This should be 2, because remember the D or the delta just means outlet minus inlet. So our to node will be our outlet, our from node will be our inlet. And then our flow I will be equal to our flow, our DH, our lengths I, our K I, our D, and our ED. Now, one thing you could do is you could make another array by, like, say, for example, pipe D np.fold in pipes D. And then what that does is it creates an array where all the values are the same. But since they are all the same, I'm just going to leave it as D and ED. Now, if issues do come up, I'll just switch back to the pipe D and then pipe ED. And then after iterating through all those, it'll return the flows. So if we run calc flows, put our heads, let's see what happened. Okay, so once again, so Python's taken these as floats, but we want them to take it as integers. So we type np int32 dot as type np dot int32. So if you run this again, all right. So as you can see, although this isn't correct, we'll get better results in a second. But what's going on here is, as you can see, we have flows now being calculated. So you might be asking yourself, well, how do we get the correct values now? So what we need to do is we need to calculate net Q, or net flow rate. And what we're going to be doing, the reason we're going to need to create these functions instead of just altering these is we are going to basically plug this function into our roots function, which we got from scipy.optimize, and it'll give us the roots at which the internal net Q is 0. Because if you think about it, the internal 1, 2, 3, the net flow between these has to be 0. Because all the fluid coming in from the external at node 0 is leaving through 4. So the Q at 0 should be equal to the opposite at 4. So if this was 1, this should be -1. Or, well, this should be -1, this should be 1. So what we're going to be doing is calc net Q. Define calc net Q. This will be taking our flows array. So what we're going to be doing is our net Q array is going to be equal to np.zeros, number of nodes. So we want each one of these to be representing a node. So in net Q, the index 0 will be node 0. And then for I in well, actually, we're going to be using a good old function np.add.apt, net q. So this is this array we're going to add to. And these are the two nodes. We're going to want to add the positive flow. np.add.apt net q. So now we're going to do from nodes, and we're going to do negative flow. Now, if you're struggling to see why that makes sense, is so the two nodes, so the flow is going from 0 to 1. So the fluid goes in, so the Q will be positive at 1, but negative at 0. So by adding to node 1, we're accounting for the fluid going in, and by subtracting from 0, we're accounting for fluid leaving that node. Return net Q. All right, so if we want to calculate net, let's do test again. Just do calc flows heads. Then do calc net Q, make sure it works. Okay, I'm just a dummy. I keep forgetting to put the S there. All right, so as you can see, what happens is, so from node 0 to 1, this much, well, so from node 0, this is how much fluid's being taken away from that node. This is how much is getting pushed into the other node, node 1. This is how much is getting pushed into node 2. So, find internal net Q. Now, like I said before, what's going on is these three must have a net Q of 0. So, and to do that, we're going to need internal pressure. So we're just going to call that internal P. Actually, just because I don't like writing words, I'm just going to call it P. So, give me 1 second. All right, sorry about that. So what we're going to be doing now is, so internal net Q at a specific pressure. So this is where we're going to be using our roots, because this is the function we're going to be using. So what's going on now is we need, not what I meant to do. Because if you noticed, there is flow going into these other nodes. It doesn't just stop. So we need to update our head values as we go. So our heads for our internal nodes is going to equal, because, so we go back to our equation. So our delta head is this. Or no, our delta head is frictional heating over G. So this equation. So our pressure over rho G plus C. So our pressure over rho G plus C internal nodes. So that's going to update our head values. And then with that, what we're going to be doing is basically we're going to be calculating our flows again. And we'll be calculating net Q based off that. So what we're doing is return calc. Now calc net Q for our internal nodes. Of our calc flows from our hits. And then so basically what's happening is, so internal net Q. So say for example our pressure is just simply atmospheric pressure, so 101,325. Turn on. Did I not run this? I did. Try doing this. As type int 32. Oh, okay. No. I think I know what's going on now. Run it as a list. So let me just look at it, make sure it's working now. So what was going on is it created a set object where it's not really able to access the numbers inside, but if we change it to a list like this, where the three are indexed, the integers now, it should work. I'll run this now. Yep. Okay, so as you can see, so if the internal pressure was 101,325, our net Q at the three nodes inside 1, 2, 3 will be 0.16, negative 0.214 at 2, and then negative 0.0694 at node 3. So we can do our result variable equal to our root function of internal, no, not nodes, net Q. And we need our guess. So I'm going to put P guess here for now. So to calculate P guess, what we're going to do is if we go back here and notice we're going to change this equation so we can solve for pressure. So dH equal to P rho G plus Z. I scroll down a little more. So dH minus Z equals pressure over rho G. So if we have rho G times dH minus Z will give us our pressure. Now, we're also going to need to make a guess for dH. So if you think about it, so node 0, dH, the head value is some value. I'll just call it A. And then a B value, but I think it's just 0 at node 4 because Z is 0 and pressure is 0 there. So basically what's going to happen is if we take the mean of these, we'll have a good guess. This is because from the entry point of the system at node 0 to node 4, the So basically, so right here is node 0, and right here is node 4. So the rest of the nodes have to have a head value in between these two. So by using the mean, we have a 50-50 shot because it's either going to be above it or below it. And so our P guess is going to be our head. Well, np.mean first, I guess. Be our heads. External nodes. Let's see. Okay, so now our P guess is just going to be our equation we found. So our rho times gravity multiplied by our delta head subtracted by our RZ, which, so, okay, so for the internal, they're all 0, so it should not really matter. All right, so if we do a result, and you see all our pressures are stored in this X value, or this X array. So our pressure at node 1 is 82,166 pascals. At node 2, it is 53,756 pascals. And at node 3, it's 73,760 pascals. We take another look at our heads. We should notice, yep. So all our heads values are now updated to what they should be. So with that, we can now find the flows that make sense. So we run calc flows again with our heads. We get a flow of 1.68 for pipe 1, 0.151 for pipe 2, and so on. So what I'm going to do now is we need a way to represent this data. So for this one, I'm going to create an object called pipes. And then just going to be a simple object. So for our init, what we need is we need a from node, to node, and a flow. We have our, I'm going to create a class variable called network, just going to be an array, or just a list. So what's going to happen here is, so self.from node equals from nodes, from node, self.to node equals to node, not two nodes, to node, self.flow equals flow. So what's going to happen now is network. So pipes.network dot append stuff. And so what's going to happen now is we're going to use the string built-in method to basically change how it displays out to the console. So for each of these, what's going to happen is we are going to want our from, which will be our self.from node, tab, R2, self.to node, and a flow of self.flow. So for pipes, let's say, so the from node was 0 to 1. Calc flows heads. So let me change this to, okay, there we go. So as you can see, so from node 0 to node 1, we have a flow of this, where it might be better if I where the units are kilogram per meter cubed. I think that's right. Let's ask your good friend Google again. Flow rate units. Oh, meter cubed per second. I am having a brain fart today. But anyways, so what happens now is we are going to create a class method. Because what I'm going to do is I'm going to create objects which will go into our network up here. Display. CLS for class. We're going to do for I in CLS.network. And I. So what I'm going to do is, so just to make my things easier, I'm just going to reset the pipes.network every time I redefine it. That way, if anything happens, it won't continually add to the network. So with this one, what we're going to do is, so for I in calc flows heads, create types. So our from nodes, range, oh, let me think about this for a second. this is used in Python 3.7, so I can't even do that. So do is flow actual, and what flow actual is going to be is just the calculated flows using our heads values. So from nodes I are two nodes I, and then our flow actual I. That's why I forgot to add when. All right, so if you look at our pipes.network, just make sure. All right. So as you can see, it's working pretty nicely. All it's left to do is just do pipes.display. And it'll give us our from 0 to 1. We have a flow of 0.168. From 0 to 2, from 1 to 2, so on. And now, what we're going to do now is we need to create another object just called node. Define a init. So we have self. So each node will have a pressure, a height, and a net flow. So what's going on now is gotta set self.p2p, not pending deprecation warnings. I hate when those happen. Self.z for z, not self.netQ to netQ. And then the same thing, I'm just going to set a network class variable to an empty list. Then every time this is called, go to node.network.append self. So what's going to happen now is, like we did before, we need to edit the built-in function represent. So I'm going to do this, we're going to return our string. So you have our node. Just realized we didn't put, just call this the index. Index equals index. All right, so we have node. Self.index. Tab it out. Our pressure. P pascals. Tab it out. Our Z value. Self.z meters. Tab it out once more. Our net Q. Excuse me. Which gives then same thing as before, display. Okay, nothing important. So display. So for I and for I in CLS.network. Just print out I. Node.network. Just set it to empty list every time I redefine this. That way this doesn't build up. No, finally. So all we gotta do now is we just need to get the pressure into an array. Zeros, number of nodes. And the pressure for the external nodes is going to equal external P. And then did I save the, yes I did, okay. The pressure for the internal nodes going to be equal to internal result.x. Let's make sure it works. All right. So now we have our pressure. We have our indexes, our z's, and our net q's, right? Okay. So, oh crap, I'll keep that. So our net q and p dot zeros, once again, nodes, and then net q at the, it's going to be equal to the calculate net q for the flow actual. Okay, that is some, oh no, wait, no, that's fine, that's fine. Just, these are so small that these are making these look really funky. But as you can see, these, the node 0 and node 4 are basically equal but opposite in sign, which is what the problem is basically getting us to. Because remember, 1, 2, and 3 you have a net Q of 0, but from the fluid going in has to go out. So the fluid going in up here has to be equal to the amount of fluid going out here. So we have our net Q, we have our pressure. So all that's left to do now is for I in range in nodes, number of nodes, we are going to create node, so index, it's going to be I, P, I, zi, and then net q. Make sure node.network, look at that. So node.display. All right. So with node.display, what we got, so we got 2,000 or 20,000, is that right? 200,000 pascals at node 0 with a net Q right there. Actually, I just realized I should probably put units there, or it's meters cubed per second. All right, it's looking nice. Then just as I showed you or told you about, node 0 and node 4 net Q will cancel out. And so with that, that should be it for the problem. We calculated our flow in all the pipes, and using that flow, we calculated the net Q and the pressure in each node. So what I'm going to do is I'm going to leave a link to this collab script, which I'm just going to name type network Exam2. I'm going to leave a link to this in the description. I am also going to leave a link to the notebook here in case you want to look at that. But other than that, I will be leaving you guys to it. Enjoy the rest of your days.